Okay, we're going to start, so if everyone could find a seat. We're going to start the final panel, the industry panel. It's been such an amazing day of conversation, and I wanted to tell you all that we're recording the keynotes and each panel session. They will be somewhere on one of RCCA websites at some point. I would give us a month. A week? I don't know, Keith, you tell me. We have recorded it, we will edit them, and we'll put them online so that people have a chance to go back. Even if you've listened to the panels, you want to hear them again. I already feel that way. So really, we thank you so much, and we're really excited for this last panel. I want to introduce Noah from Autodesk Research. We met probably a couple of years ago, but realized that our backgrounds and our alignment of our value systems, and she's in East Bay or Berkeley too. So we're thrilled that you're here to moderate this final panel. Thanks.
Thank you, Margaret. It's such an honor to be here. I was a panelist last year and learned so much from the event, and it's my honor to be here moderating the industry panel this year with our distinguished representatives from industry. I think you're really going to see a different angle on many of the questions that have been brought up in earlier panels and discussions. Before I invite them up, I just wanted to share a little bit about my background. I've always been fascinated with materials, and I studied sculpture at Yale University as an undergrad, and I just loved working with physical materials, and I was curious about why someone would choose a specific material for a particular project. And at the same time, I was really interested in emerging technologies and manufacturing processes. So how you would leverage those materials through different processes and workflows to get the output that you want and create something with meaning. So I did my MFA at UCLA in Media Arts and Practice and started combining organic materials like honey and wool and clay and seeds with more computational processes and emerging manufacturing technologies. And after that, I continued my creative technologist art practice, and I also taught at UCLA in the architecture department and the design department for almost a decade. At the same time, I pursued a PhD where I focused on technological ethics, so really looking at the other side of, why we're making decisions, what is our agency when we're using technologies, and how those decisions proliferate out and impact communities and the planet. I was not expecting to become a part of industry, but life brought me back to the Bay Area, and I started working at Autodesk, where I am a senior research and design engineer. And I work across different research projects, from robotics to performance-aided design, and now even media and entertainment research. But one of the things that I also spend a lot of time doing as the additive and hybrid manufacturing SME is managing our additive fabrication shop. So I oversee about 30 machines and also get to decide what materials we bring into our space at Autodesk. And I know this sounds kind of mundane, but it's been a really interesting lens into the same question that I started with, which is, why do people choose certain materials? And because we're not a production shop, we're a research organization, we have representatives from academia, like CCA, which has been incredible. We also have nonprofits. We have groups that are making autonomous vessels that grow seaweed to absorb carbon. We have groups that are trying to create a kind of Noah's Ark of coral to save those populations. And then we also have startups that are creating new companies and new business models for solving some of these problems. At the same time, we have our researchers. So I get to see all of the different kind of approaches and values and scales of thinking about why you would choose a certain material for prototyping something in your project. And I get to invite new materials into the shop. I also work with our environmental health and safety team to say, no, we can't bring this in here, or maybe this is harmful in some way. And there are also some compromises that have to be made. Like early on, when I started, I really wanted everything to be as sustainable and circular as possible, and I had these really high aspirations for doing that as quickly as possible, and then faced the pressures, no, we need to make this UAV that complies with, these standards for flight and governance, and I think that, no biomaterial that's certified will work for our project. So, I have to balance all these different needs at our organization in our shop. So, I think one of the most exciting moments in my experience at Autodesk was working with Nagar and Margaret and their teams to bring biomaterial printing into the additive shop. And we set up a little ABB 120 robotic arm with a clay extruder, and there have been experiments over the years to develop that process. And it's just wonderful to see the energy and dedication that the faculty and the students are bringing to that work, and to see the larger conversation unfold here. So it's a little bit about me, and now I would like to invite our panelists up. We have Emily Alvarez, Eva Haar, Bill Chrysler, and Francis Sam. Great, so we'll start with introductions. If you could introduce yourself and also what industry you represent, and if you could share at least one case study of a biomaterial that you've worked with or you've worked with policy related to. And Emily, if you could start us off.
I changed my slide, but I guess it didn't work. So, sorry about that. What I had up here, this was this image from our poster that we made with Eric, but I think Francis has the whole poster. So between that and also wanting to, after all the inspiration that I had from the earlier conversations, I had changed my slide, but it's okay. This is my fault for doing things at the last minute. Because I work in government. I work for Stop Waste, which is a local government agency in Alameda County. The reason why we're here as kind of a waste agency is because we have seen all the issues that happen with the linear economy. In general, the things that we consume every day, or not every day, things that go into buildings that last a really long time, are largely not meant to have a second life. And so what happens as a result of that is just, again, an endless kind of amount of waste. We spent the past year about doing a waste characterization study in Alameda County, where we went to over 10 waste facilities in the county, did over 650 samples of waste to kind of figure out what people are consuming, where those things are winding up, to help us understand what can we do better to reduce that. And it's really, you see some of the obvious things about how people still throw away food in the landfill and things like that, but one of the things that stood out so clearly to me was that even if we took everything that could have been composted or recycled or reused out of the landfill, we would still be left with so much material that right now has no other second life, no other home. It cannot be composted, it cannot be recycled. And so, it's a lot. Sorry, Margaret. But it's kind of the second largest kind of percentage aside from compostable organics, though, of all the materials we sort of studied. And so what that means is we do have to think kind of at a different level, because if those products nothing can be done with them in their current state, then we have to think about how we redesign them, repair them, reuse them, remanufacture them, because we just need to do better, to think differently. So wanted to bring us back to that idea of why biomaterials is even something that we're really talking about. I'm glad that we've all decided it's something to talk about, but this is one of the reasons why, because we want a material that at the end of life, we can do something with it. And it presents so many opportunities. And one of the things we also found, which had a picture of, is compostable plastics. And that was kind of my example of when we try and think about something in trying to find a solution that seems good, but we're not thinking really regeneratively, and we're not looking down to that biological level that people have been talking about today, and when we also have kind of a discrepancy between a product that seems like a good idea and the kind of real world where that product exists. Because what happens with compostable plastics are they leave behind microplastics, and also they are usually not fully compostable in an actual compost facility in the time that that compost kind of exists and cycles through that facility. So we have now all these compostable coffee cups and compostable forks and bags, but they're waste, and they're actually contaminating our compost streams and making it harder to create quality kind of compost and organics. And so what can we think of then as like an actual real solution? And so that's at the product level, but then it scales up to the building level and things like that. And someone else, I think at one point, I'll close with, said, I forget who, the last panel said about like alternative careers for architects. And so, I thought I was going to be an architect. I did that to become one. I have a master's degree in city planning, and I sort of do some policy work, I guess. But just to again touch on how it can be such an important jumping off point to so many other things in problem solving in our world.
Are there any? Is this working? No. Here. Are there any good compostable plastics? Or they're all bad?
Oh gosh. No. Wait a second. Okay. That's a really complicated question. But I think this is a place where, again, you can, I would say at the moment, not really. But that is where we actually thought about, okay, how long in California or in other places does a compostable plastic have to break down in a facility? Then that's, again, like, or bring industry along and say, why can't this work? So I just think, again, it's an example to me of like a good idea moving in a solution, but in the real world isn't working.
Because my team brings compostable plastics to the table all the time. So I'm Yves Behar. I run a Fuse project, which is maybe 100 meters kitty corner from the building here. We've been in that building for 13 years now. And we also have a small studio in Lisbon. And that's where we do a little bit more experimental, material-based projects, more European-based projects. But overall, the composition of our work is, I would say 50% corporate work for bigger entities, and 50% startups. And the opportunity to work with startups is fantastic because things happen quickly, contrary to some other projects. And startups don't have a choice. They have to put something out in the world. So that makes it fun, fast, furious, and I love risk taking. So it's part of the culture up here. This is a project that we did in Portugal. This has actually been outdoors in Lisbon for 6 months. And it's part of a project that essentially is a way to kind of show and demonstrate the use of cork outdoors. It's sponsored by Amorim. Amorim is the largest producer of cork in the world. Portugal produces more than half, so more than 50% of all cork in the world as a material. And going to the Amorim factory, I mean, it is a massive sort of facility. And what you see is gigantic cork rolls and cork in every form you can ever think about. You also see gigantic piles of recycled materials that are mixed in with the cork in order for the cork to have different performance. And if you want me to talk about cork, I'm gonna take up the entire hour and a half. Because it's a somewhat recent discovery since we've been at the studio in Portugal. And it is really the material from the past that's made for our future. It is used absolutely everywhere today already. Every gasoline engine has cork-based gaskets. It has amazing compression, it has amazing sealing sort of abilities. It has memory. It has all these things that if you were trying to invent a material today, that you would want all of the capabilities of cork to have, you would not be able to invent it today. So it is truly incredible. So I'll just go quickly. Cork is the bark of trees that gets removed every 7 years. So when you think about a tree, 200-year-old tree, it will produce cork about 25 times, a whole sleeve of cork there. That means that it is the best carbon sink you can think of. It's not just a tree that grows once, but every time you remove the bark, it sinks more carbon. So imagine any kind of material that, or living structure today that essentially continues to sink carbon over its lifetime. It's pretty amazing. It grows on sand, needs no water, or very little water, only in its early years, but there's just enough in the south of Portugal of water for the trees to grow. It's fire resistant. A friend of mine during the fires last year in Portugal lost every piece of vegetation on a gigantic property, but the 1,000 cork trees on it did fine. So it is, climate change resistant, I guess you would say. And then as a material, it's incredible because it's insulating in terms of sound, insulating in terms of humidity. It is also, so it is a material you should use really for insulation, and more and more architects and projects are using that material for insulation. I forgot the name of that tragic accident in London where that building that burned down. And Grenfell. Exactly, 60 plus people died. They didn't die from the fire. They died from inhalation of the material that is supposed to protect you from fires. And so if cork had been in there, if they had used cork as an insulation instead, cork will resist fire for an hour and a half plus, so it's plenty of time for people to get out. And essentially the cork doesn't produce a dangerous smoke, so a much better solution there. But cork is also a material that can be mixed with a lot of other things, so everybody who's wearing Birkenstocks has experienced cork under their feet, mixed with recycled EVA or recycled rubber. It is a material that can be used, as we demonstrated here. This is a tile system. It's these octagonal, hexagonal tiles that we can color, we can place over curves. The idea was to create a universal tile that can cover flat, convex, or concave environments. So we made this little tower at the entry of Lisbon. It's actually amazing. It's complete. It's open, pretty small, but as you walk in the hot summer of this part of Europe, it actually is slightly cooler inside, and it's the sound insulation is amazing. So we started to apply cork to a lot of the projects we've been working on lately. We're building a new car company at the studio called Tello. It's a pickup truck, sort of full sort of size pickup truck in terms of capacity. So you take Ford 150 equivalent, and you have the same room, leg room, headroom for 5 people inside, same cabin, same truck bed, 60-inch truck bed, front to back. The Tello is the size of a 2-door Mini, 152 inches long. And we're using cork, oceans plastics, recycled oceans plastics on the interior portion of the vehicle as well. And the reason for that is obviously it's lighter, it's sound insulating, it does all the things that we love it to do. We've also recently used cork on a super yacht that we have designed, the first hybrid solar electric super yacht. Its propulsion allows it to cross the Pacific, so twice the distance of the Atlantic, without refueling. And so using 100% electric power, which is the reason for these types of projects is that they are precursors to how the commercial shipping industry, and other sort of boat industries would be using this type of power. And then the range of our projects is vast. I mentioned the super yacht for one reason, is because the other project I'm super excited about that we're starting on is toilet paper. So the contrast between these two extremes is something that I'd like to talk about. And I'm learning a lot about toilet paper, so I love the fact that this job that we have, which is we're invited to really look into so many different types of industries, just becomes a school for me. Actually, I used to teach here, so I like school. But I've learned, for example, that with the changes that we're experiencing in the media, etc., recycled toilet paper and recycled paper is it's hard to find paper these days. People don't read magazines and newspapers as much, so there's not as much paper to do recycled paper products. But what do we have a lot of today? What are we consuming like crazy? Cardboard boxes, but that's brown, and it turns out brown toilet paper is not the most exciting stuff. No, fast fashion. So when you think about fast fashion, we're consuming, unfortunately, a ton of it, and you can make paper with fibers, natural fibers from fast fashion, for example. So that was an interesting discovery. The other one that is even more interesting, I find, is the fact that when you go to the market, for years I've picked up and bought the sort of cheap recycled toilet paper. The one that has just one, that's like one sheet or 2 sheets thick. And I'm like, it's not a great experience. It's kind of a plain thing. But for years, I'm always like, okay, what's the choice I can do as a consumer? Let's pick up the cheaper, simpler, recycled toilet paper. Well, it turns out that the luxurious toilet paper, which has many plies, many sheets, is very soft. It turns out that people use the same amount of paper whether they're using cheap toilet paper or the expensive one. So let me explain. When you use a cheap toilet paper, you use typically 6, 7, 8 sheets. When you use a luxurious toilet paper, you use 2 sheets. So in the end, it's the same amount. And this is, I think, the challenge that we have with materials, biomaterials, etc., is the fact that if the experience becomes inferior, we just don't use it well. And so my sort of interest has always been about how to take sustainability, sustainable products, sustainable materials, and use them in ways that makes you feel you're actually getting more value, not less value out of them. And I think as a designer, when I can show that, when we can make that real, there's a huge sort of aha consumer satisfaction that comes with that. And also, you just get to forget that it comes from a different source. You're just enjoying the product as is. And so I think that's an important role I think we can play in terms of creating that acceptance.
Thank
How much
you.
longer do I have?
I think that was great. We'll get deeper into case studies in a moment, but I'd love for Bill
Thank
and
you.
Francis to introduce themselves.
This on? Yeah, great. Well, I'm not a designer. I started my business probably before most of you were born. And it was because I had worked in a fiberglass boat building company for quite a while. And I thought to myself, when that business was sold, I was either going to go back to school and do something else, or I was going to start a little company, which I did, trying to find other things to do with this, what I thought was kind of this amazing material. And that led to opera sets, movie sets, all kinds of signage, and different shapes that are complicated and that benefit from the lightweight and the strength of these composite materials. When we started getting calls from contractors and architects, it was to see if we could make replicas of historic building ornament. And at that time, a lot of the parapets, and to this day still, that were built in the early part of the 1900s were failing because the terracotta was being forced to crack because of the iron rods that were inside. They would expand when they rust, they would crack the terracotta. And they literally had pieces falling to the ground that were hundreds of pounds from several stories up. The one example was a Pac Bell building here in San Francisco, the headquarters building, not too far from SF Loma. And they had something like 600 pieces break and fall, most of them fall during the Loma Prieta earthquake. So we started getting to talk to architects. And as we did, when we told them what we did, they couldn't find the door fast enough. I mean, it's fiberglass, it's plastic. We don't want to have anything to do with that. Get out of here. So I thought, well, this is not going as well as I hoped. Maybe I better learn a little bit more about how to understand their concerns and to try to figure out where we really stand. And as I did, some interesting things evolved, and that was that because we're working in the environment where we're a manufacturer, and everything we do has to have a warranty, and everything has to meet the building code requirements, we found that being a little too innovative sometimes can not work. I mean, you just can't get somebody to pay for it if you can't guarantee it for a certain period of time. But an example of a parapet was and our success at getting the job was the old Ford Motor Company dealership on Van Ness Avenue that has the two bears on the parapet that maybe some of you have seen. That parapet was gone. It was taken off because the building department made it take it off. But the developer who wanted to renovate that building wanted to put it back the way it was. And so they talked to the original sheet metal guys, and that wasn't going to work because, first of all, there's nobody left that did that kind of thing. But second of all, they learned from over the years that sheet metal joints, solder joints don't work. So then they started thinking, well, we'll do it in terracotta, but the problem with that was that the weight of the terracotta was so high that the engineers wouldn't let them put it on the parapet. It was too weak. So we came along, we said, well, we've got a material that weighs a tiny fraction of any of those things. And how about that? And the engineers looked at it and they said, well, yeah, okay. I think if it weighs that much, this parapet is fine. We'll be able to leave it. So instead of tearing off the parapet and rebuilding it and putting a whole bunch of steel inside it, we were able to hang an all FRP parapet or cornice off that building. And that was about 30 years ago, and it looks like the day we put it up. So that's one example of a material that at first glance you might think is the wrong material, a material you may not even want to use because it's plastics, has some advantages. Another good example is the SF Loma facade. And I think maybe a lot of you are familiar with that. It's the addition to the SF Loma building. And one elevation of that building is this made up of all these kind of ripply, wavy panels. Well, there's 700 of those panels on that building, and there are no two of them the same shape. So they were about to give up on that idea, and we were asked to look at some other part of the building. And when I saw at Snowheada's office in New York, I saw this mock-up of the facade, and before I left, I said, well, what about that? Who's doing that? And their answer was, oh, I don't think we're going to get to do that because it's just too complicated, there's too many molds, and it's too expensive, and on and on. And so in fact, that meeting in the conference room over there is everybody's trying to decide what we're going to do about the facade now that we can't do that. And I said, well, have you thought about composites? And they didn't even know what I was talking about. And I convinced them that it might be worth considering. And I told them, you know, molds are expensive, but if you only use a mold one time and you use it out of a recyclable material, like an expanded polystyrene foam that can be melted down and made into, usually I can paint it quite at baseboards. Build baseboards. Then you know, maybe it isn't so wasteful, and also maybe it isn't so expensive. And so one thing led to another, and that facade ended up being all composite. And because of it, the thickness of that shell, that surface that you look at when you see that is about a little over 3/16 of an inch thick. So little material that it was light enough that it could be fastened to a unitized wall panel system instead of a stick-built wall that had hundreds of penetrations to support a steel frame to carry the weight of the GFRC. So one of the consequences of using the plastic was the savings of over 1 million pounds of structural steel in that one elevation, plus several months of the construction schedule, which is expensive. And so, again, I guess the point I'm trying to make is that as you peel the onion back a little bit, sometimes the answers are not the obvious answers. Sometimes the answers take a little out of the box thinking. And I'm not entirely sure what biomaterials are. Maybe our resin comes from oil, which as best I can tell is a biomaterial. But you know, it's not so good for gasoline, and it's terrible for disposable plastics. But if for a building panel, it's expected to last for 50 to 75 years. Maybe not so bad. But the only problem is that very rarely do we get a job because we have the greenest solution. And we usually look at that as an option because it also helps us tell us whether we're going to be competitive. Ironically, a greener solution in our world, where we're doing mostly facades, is also oftentimes the most cost-effective, the most efficient solution. Not just in terms of energy, but in terms of dollars. You put less material on something, it's going to be maybe less expensive. So the only time that a client has ever prioritized environmental impact was the Monterey Bay Aquarium, which we've done a lot of work for. And aquariums are really difficult material systems because they live on the salt water. And there's nothing more difficult than salt water on a material. Composites haven't been, instead of not being affected by that, or all the boats would sink that have been in the water for too long already anyway. So they, although our solution to this special tuna tank they had down in there at Moss Landing was more expensive than the shotcrete solution, there were some advantages they liked about it. It's easier to clean, less biological problems on the surface. But still, it was less expensive, the concrete, and they thought, well, you know, what else have you got? So we did a life cycle comparison of the shotcrete versus the FRP. And even though our material had to go to the landfill, and the shotcrete could theoretically be recycled, the energy it took to tear that shotcrete apart, take the steel out of it, grind it all up, haul it to a place that can do that, and then find a customer who wanted to use it, was far more than the landfill of these very lightweight, very thin composite parts. So in that case, we ended up getting the job, even though we were a little more expensive, because the client took the time to peel a couple layers of onion back and discover that what seems obvious at the beginning maybe isn't the case. So, like Eve, I could go on for like, oh, I bet you I could outlast you.
Thank you, Bill.
Hi, I'm Frances. Really close. This is working out. Okay. So I work at ERIC. We're a global engineering and design firm of the built environment. Many of you will become architects, and you'll be our client. So I have the pleasure to be the circular economy leader for our Americas region. And what led me there, actually, I started off as a structural engineer, and I realized the enormous, carbon emissions, how carbon intensive the primary materials for structures were to our environment, and I wanted to focus more of my energy in combating that. So I actually got to move over to the sustainability team with a focus on materials and sustainable materials. And in embodied carbon, it's really exciting. People actually know what it is now compared to when I started to make that, I guess, have that realization at the start of my career 20 years ago. But I also think that the idea of circular economy is really important and offers not only a path to decarbonization, but also helps us realize other aspects that are really important for resource consumption, for waste reduction, and supporting the things that Emily was talking about of thinking about the lifetime and the biocompatibility, especially when we talk about bio-based materials or biomaterials in general. So I'm the circular economy leader. We work with Ellen MacArthur Foundation, and as you probably know, they are considered the leaders in really pushing these ideas of circular economy, and the three tenets really being eliminating waste and pollution, circulating the materials we have for as long as possible at their highest value, keeping them in circulation, and then third is promoting regenerative ecosystems and thinking about how we're really contributing and reusing these nutrients in ways that are like our ecosystems, just naturally regenerative and not degrading. So with those three tenets, I think it's been a really great framework and journey, I think, with getting to work within the built environment and particularly with architecture, and just thinking about all the different kinds of materials that can be alternative sources compared to our traditional materials. And also what I appreciate is the just having to work across different sectors and looking at the enormous amount of waste in our linear systems, and where we can start looking at the waste from some systems and become nutrients in others. So for example, like the display that you might have seen over in the exhibition, all of the agricultural waste that we see generated, and stock waste has helped to do a lot of that research and characterization, and seeing an opportunity, especially in California, to channel that into our construction materials, which not only helps reduce the waste and subsequently the emissions from agriculture, but keeps us from using raw materials that would have high embodied carbon in their making, and we can replace them with this waste product instead. And then in the end, if we can really unlock, really think about the end of life and how to utilize and put these materials together to make them have successful end of lives, to go back to the earth, be compatible, or re-enter into products again. And so actually, I think about the FRP, and we've had great pleasure working with, not me personally yet, but my colleagues in facades. And FRP, I think, is such an interesting, it's basically a composite, right? And you have a resin and a fiber, or a matrix. And you have to, one component gives structure and form and shape, and the other one holds it together and keeps it, durable and if so we did my colleagues in the Berlin office actually did a collaborative. This is also, and you'll find it in the booklet and up in the display. It was called BioBuild, and it's an FRP facade panel. And they took on the challenge of, could this be entirely bio-based? So they came up with, looking at a whole bunch of different natural fibers, and then a whole bunch of different oils, and just experimenting and getting to play with that, and then eventually form a full-scale prototype and of a facade panel, and in a similar way that you would make FRP. So I think there is potential here, but it will take a lot of collaboration, and I just get to be in the space of seeing all of these opportunities, and then kind of pushing them amongst our engineers and designers, and stress testing them that way, and working with our materials consulting team, and really trying to help get these solutions to market.
So we already got some great examples of specific materials, but I just wanted to see if there are other specific biomaterials that are on your radar that are having a big impact or have the potential to really transform the industries that you're in or working with.
You asking all of us, or?
Yes.
Well, let me start, because I can take off on this comment about natural fibers and bio. So we would love something like that. And where we run into a problem is with the building codes and with the acceptability of a customer. I mean, at the last panel, there was somebody who asked, well, if you were introducing a new material, and what would be the first person you'd put on your panel? And they asked everybody, and nobody said a customer. And I'm kind of stuck in my business, because if you don't have a customer, you're nowhere. And then the next guy would be a code consultant. And so, as exciting as a lot of the, and we love to, I mean, we did the thing with Autodesk and then the Cillian Core, and we're working with them on that, and we think we can get that through the process. And so we're kind of scratching around, looking everywhere we can for those kind of opportunities. But it takes people like yourselves to develop an idea, and then materials scientists to work on how to make it, comply with codes. I mean, fire codes are a huge thing for natural fibers. They're like, they burn. And anyway, enough of mine. You must have something.
Well, although I'm sure you also have something. you say. But building off of that, I mean, so part of my role also is working with local governments. A lot of what I do personally is on energy code trainings, but the same we do for building code. And so we'll support cities that want to adopt standards that are more strict than the California building codes or energy code. But also when you do have something that comes through that seems really obvious but is far into a building department, we'll also kind of help out with that or figure out what assistance they need or even how a jurisdiction can encourage that kind of design in their city. And so one that kind of builds off of that, but is also a question that you said is like going back to something perhaps basic, but just wood and high-rise wood, and how sustainably managed forests and sustainably harvested wood is a biomaterial that seems obvious. We're very used to building with wood, but even just introducing that as like a CLT in a high-rise project is something that building departments were very skeptical at first. It didn't fit into the fire code and things like that, and so even just the work to get very familiar things in a different application through code. And the city of Emeryville has allowed some extra density bonuses in their planning code for building with high-rise wood as a way to kind of encourage it. So there are kind of creative solutions where we can have government work to figure out some of those things, but the reality is that a lot of building departments are pretty conservative. I think someone brought it up before, they really see their job as kind of life safety. And that's good, right? I mean, we all like to, sometimes it's easy to kind of say it's too much, and sometimes it is. But working at a permit counter at a city several years ago, you have a different respect where it's easy to think that if it's not, because most of our buildings don't fail, maybe sometimes it's too much, but if it was your building that did, you would have a very different perspective of it. And so you kind of do have to respect the building officials who are really seeing the fact that they think they're kind of saving lives. And how do we work with them, bring them into the room, train them, help them do their job, instead of just kind of being dismissive of it.
Thank you. Know about specific codes or policies that are hindering or really helping the development and implementation of biomaterials. Francis.
Waiting for the light to turn green.
Yeah, actually, okay. Being in an international firm, I often see Europe doing things ahead of these matters of breaking down barriers and having supportive policies. And on the financial side too, right? Like that's a huge part of it. There has to be a business and there's a driver there. So some of the things I've seen really helping is just at the planning stage or in early design, having requirements that force the project team to answer to how are you going to help make this a more sustainable project, and what are the tenets of circular economy that you're fulfilling, how are you decarbonizing, all of these things I actually have to submit with their building application. So or the planning application. And so slowly, I think we're starting to see some movement in the US. I think it's starting with decarbonization, not quite really the circular economy yet for the buildings industry. And it's mostly coming at the state and local levels where we're starting to see policies in procurement of materials, and then kind of pointing and trying to encouragement to have project teams consider bio-based materials before the traditional. So slowly, but yeah, Oregon, Colorado, in California we have the Biclean, and then like Ellen said, the Emeryville density bonus. So there's signs, but I think it's really at the local levels and then maybe state, and not well, especially now I don't really see what's going to happen in the federal. Yeah, federal, I think it's been more of the investments in some of the regulating practice specific sectors and how to make them differently, but not, haven't seen a lot of investment in bio-based as an alternative, like, I think
Thank you. Bill, I'm curious about your perspective on this, since I know you've gotten certain materials approved that weren't in use before and you're working towards that now. What is it like to try to introduce a new material, and what is the timeline and the hurdles that you face?
Thank you for asking. And I'll try to keep this brief, but if you want to change the building codes, you got to set aside about 4 years of your life to get per paragraph. In our composites industry, there's a bunch of small companies, and I got a fairly small company, but there's other even smaller companies that make fiberglass things for buildings. And up until 2014, most of what we were doing was illegal. And the only reason we were doing it is because the building code officials themselves didn't know enough about what the rules were. And we had one fiberglass company, and fairly good sized company. I mean, probably the biggest of all of us in Texas, who was making church steeples. And he made 2,000 church steeples a year, none of which met code because they were combustible, and the code requires anything above a certain height to be non-combustible. So he was a little shocked when he found that out, and we hired a code consultant as a group, as an industry association, which is really important. You can't do this on your own unless you've got a lot of money. And we petitioned the code. And the interesting part about that is that the guys who vote on whether something passes or not are the building code officials. And the building code officials are not scientists. They're guys who are inspectors, firemen are automatically part of the building code. I mean, these guys are great guys, and they will lay down their life for you, but they're not trained in the technology of materials. So they rely on these experts. And if you've been to a code meeting, there will be this room full of hundreds of people that are there because their companies or their fire department or their cities pay them to go there, and it's a great party. And up on the dais, there's the inquisitors. And they don't have cone-shaped hats, but they might as well. They're the guys who basically argue out what's going on. But it's all done ahead of time. One guy is the code consultant for the steel industry. Another guy is the code consultant for the wood industry. Are there any code consultants in the room? Any building officials in the room? Good, okay. And they kind of present their case. But there's all these deals being made behind the scenes. Well, you want to get your fiberglass passed? Well, into the code? Well, I'm trying to get this polyiso urethane foam insulation through, and I'm having a hell of a time with this. So, well, so it's a game. It's not very scientific, in spite of the fact that we end up with some of the best fire codes in the world, and right now there's some real concern about the fire codes in Europe because of the fires that they've had, and we really have, thank God, knock on Jesus. Anyway, the point is that the codes are capricious, they're heavily influenced by the industries that hire the officials that sit up in the front on the podium. And excuse me for being so cynical if I'm embarrassing anybody, but I think that's kind of how it works, and it's hard. And yet, we got it through, so there's some justice, I hope, and that's how that works.
Thank you for sharing that perspective, Frances.
Yeah, to build on that a little bit more. But I mean, I feel like that there is a realization that it's so tedious and laborious and just takes years off your life, right? Sitting through the testimonies and so right with the hearings, basically hearings to make changes. But recently, I feel like I've seen standards actually getting written faster and a move towards more performance-based standards. that gives me some hope.
Yeah,
And
right.
actually having
It's
more
true.
performance-based standards gives a lot more flexibility because a lot of the barriers in code right now are because they're so prescriptive. And if you don't meet every, little aspect of them, then you don't fit anywhere. And, but having something, so those two, seeing them develop faster and then move.
You're right, and it's it's environmental issues that are driving this because it's very disruptive. Nothing's changed for hundreds of years, and now all of a sudden everybody's worried about environment. And that's got the whole code thing destabilized. And now is a good time.
Francis, could you explain a little bit more this paradigm shift to the performance-based standards and what that difference is?
Yeah, so so prescriptive being where that has to be made up of certain materials, it has to have certain proportions, or it's almost like a recipe, and then of what comprises an acceptable building product or a system.
Listed in the code.
Yeah, and that's official definition, and then it's quite limiting. Whereas performance-based is talking more about, here are more, what's the intention, right? And we want to see that you're, often through testing, often through demonstrated testing, that you're meeting these attributes that we need, instead of just being, following a recipe. Yeah. It can mean, there's still rigor that needs to be applied, like the testing, and then it also then means, okay, maybe we're missing a lot of different kinds of tests too, so then we have to go create the studies for those tests. But it is a shift, like a paradigm shift that should open up the conversation.
Thank you. Safety has come up quite a few times in this conversation about code because that's mostly what they're protecting is safety of occupants. Are there other dangers that might be introduced with biomaterials that are a little bit less obvious than just safety issues?
Again. I guess a lot of times, because I'm in an engineering firm, we think about all the different layers and all the different systems that are in a building, and that every component pretty much has a different set of performance needs. I guess when you say besides safety, maybe if we think about it like on the risk scale, right? Like that we have our low risk types of building products and then higher risk. And then especially because I'm coming from structures maybe, but durability is a huge factor, which is often a challenge with bio-based materials because they're naturally meant to, go back to the earth and break down and under the elements. And whereas we're trying to create things that will last, longer than how they were in their natural form. But that I think is where just really trying to think about you've heard of the idea of shearing layers, but that's another huge concept in circular economy that if you could think about the layers of your building in these groupings that are defined by their service life and how often they need to be replaced, that's often corresponding to the durability needed, then it's a little easier to think of, okay, what's possible, what are my options of something that can, that would naturally expect to replace in 5 years versus 50 years, and then you have a very, you can deal with the additional performance requirements just for those and not have to think like, I have to come up with a solution that's going to work for all. I think that's maybe one way to help break it down and approach the challenge.
Maybe it's not a safety issue, but something else that just comes to mind is, again, just thinking, this sounds really simple, but thinking very critically about like the problem you're trying to solve, and not always coming at it from like, having the tool or the solution already at hand. And I think it can be really obvious, really easy to do that, perhaps especially in academia where you're like studying one thing so intensely, which needs to be done, but you want to make sure that you're not like leading, trying to come up with kind of solutions or problems that is like a solution to. And so I bring that up because in certain kind of biological cycles, when we've said kind of highest and best use, like there's a lot of things that maybe are organic matter, but like compost is actually really important. And so maybe there's certain things that like, that's really what we want to do with it. And so I think when we need to, when you're parsing out kind of like what solution you're trying to solve, is it because concrete is 7% of the world's greenhouse gas emissions? And so what's like a good substitute for concrete that is just as strong? And maybe it's a bio-based solution, but it can also be changing the way that you build concrete, because sometimes we over-engineer things to just use less of it. So there's, you know, a good, better, best for a lot of these. And so sometimes, so I think just being really critical about kind of the problem you're trying to solve and what are the kind of different versions of that solution, and having to look through the life cycle of something. Because also, maybe we're coming up with a material that could be more compostable at the end of life, but all of the kind of, all the things we have to do to it up front maybe are really carbon intensive, really energy intensive or something. Or we've got this great biomaterial, maybe at this point in time we don't have an appropriate bioresin for it, and so maybe it still gets coated in plastic, and then maybe that's better over a life cycle from a conventional material that had to be mined or manufactured. But so I think again, we need to start really thinking regeneratively and over the life cycle of something, so that we don't keep coming up with these sort of partial solutions. And partial solutions aren't bad, right? Like we can find substitutes that are better, but I just really implore us to think as big as we can when we're trying to solve these problems, because I think we wind up, again, these kinds of like, this one sounds pretty good, and then you kind of find out that there's you know, a negative in one part of the life cycle, and maybe just sort of stop there.
I've worked a lot less in architecture and environment, so I have less examples, but one that comes up to mind is, and it's going to go back to concrete and cork, but is the ferry and bus terminal in Lisbon is built out of a mixture of concrete and cork. So basically, the cork is inactivated within the concrete. The architect is Alvaro Siza, who is the godfather of architecture in Portugal and beyond, and modern architecture. And by mixing the two, they got to a concrete that's 50% lighter, which means that structurally, you save 50% of the cost and weight of the steel, etc., to hold the building up. And so, you know, what I often wonder is, well, could you even do that here, right? Because maybe the laws or the sort of flexibility around this kind of material isn't there. And I have found that that is a barrier to people innovating. Is often there's very little ways for a small company or for anyone who doesn't want to spend 4 years working on a paragraph to go ahead and do that. You know, one example in our building here on 16th in Carolina is we installed this very novel ventilation system that allows us not to have we thought AC and heating or in the building. We were told this is an absolutely great system, it's used all over England, very innovative, but it will take a lot of money and about 4 years to get it accepted. So it was very interesting because the bus terminal downtown San Francisco was South in Soma was going to use the same system, but there were, the sort of final permits were 2 to 3 years ahead of us. And so we didn't have a choice to wait for that to be authorized. What we did instead is we put them up anyway, and then we put a full AC and heating system in place to be at code. So we basically did both, but we rarely rarely turn on that system, and we just use the ventilation up there. And so I really feel like often you're sort of constrained to not innovate based on what's available from a code standpoint or even from a material standpoint. I remember one interesting story. We did a lot of projects with the mayor of San Francisco at the time was Gavin Newsom. We did a lot of projects on sustainability approaches, different aspects, and one of them was the biodegradable plastic bags that the mayor in San Francisco pushed for back then. And what was so interesting is there was nothing available. The industry did not exist until San Francisco said, well, it doesn't exist, but if we push for it, somebody's going to make it. And so sort of creating basically the mayor created the market for biodegradable bags. Now, I don't know if you're happy with those or not. but it's for me, it's an example of the responsibility that political leadership has, which is to incentivize innovation by asking or demanding for it, which happens rather rarely, I think, these days.
What are other incentives or accelerants that could move this approach forward?
One, you could get the engineers to lower the safety factors on all the buildings.
Well, but there's definitely, I think, like, when your point, there's like so much over design and so much like, well, we're not gonna take this, it's not worth it to sharpen our pencils, let's just rationalize, which is like on where you make everything the same, to make it easier for the contractor as well. And so your capacity is much higher than the demand for most of the area, that region that you just assigned, the same dimensions, or apply the same design to. Yeah, I think that's more maybe a culture change that is definitely being discussed among senior engineers, I see. But I think it'd be pretty hard to try to force that through policy. I think it actually needs to start as a design mentality and approach, and a shift that is almost more peer pressure.
Yeah, I don't think it's quite as simple as just lowering, but I think the point is that we're sort of in the middle of all of that because we buy materials who have specifications that have the factory who makes those safety factors built into it. And then on top of that, the engineers put their safety factors, and it basically boils down to liability management. I mean, if somebody told you that there was no way you would get sued if there was a problem, then then it would be a race to the bottom. That would be bad too. But if there was some way to sort of, and maybe, I hate to say this, but maybe computers are the solution because they can do these sort of like digital twin modeling of entire buildings and start looking at how the whole building will perform. And that's the risk you have. You're worried not so much about whether this particular thing is going to work, but how does it work with all the other things that it has to interact with. So
that's definitely the case in automotive design right now. It used to be that you get very expensive wind tunnels to test, for example, the performance of your vehicle. Now it's all done by software. Crash testing is done by software. You used to have to crash dozens and dozens of cars before getting anywhere. Now you can do 95, 99% of your crash test through software as well, which is a huge saving in time, and money and materials, and you get to the same results. I mean, to illustrate that a little bit, there is an experiment that was made recently that had essentially a car made out of Legos. And they crashed the car made out of Legos, and they filmed it in very low speed, high resolution, to look at what happens to the Legos. And they replicated that with software, the same car, the same crash, and it is absolutely mind-boggling. The Legos are almost spinning at the same speed as the video in the software. So that is, that obviously is a demonstration of the strength of the software today. These software tools, in order to get faster to the kind of outcomes that you need in order for materials and processes to show up, more often and shorter time scale.
Yeah, I think it's come up so many times, and maybe it seems really obvious, but just collaboration too, and even just changing the way we're thinking. I mean, here we're at a school, where we're even talking about bio-based materials, and I think just getting it out of our heads as we're even training young architects or in our own practices or anyone we talk to, that just because we are very used to building with steel and concrete doesn't mean that is how things always have to be built. And allowing that kind of experimentation and that openness. And maybe while we don't want to get too real life sometimes as we're training young architects because we want them to be very creative, thinking about what certain material palettes or other changes, or what if you didn't build a new building, at all. How can we really just make that questioning of the way we've always built things into practice, so that this isn't something that a new architect has to unlearn in 10 years. They're coming into the industry challenging how these things are done. And then even those people who've been working on this stuff for decades, just not being afraid to keep challenging, even if it takes 4 years, because then maybe eventually it won't take 4 years. Or the Marin, in 2018 is when the Marin concrete code stuff started, Francis, but from a grant from the Bay Area Air District, Marin County was working with Stop Waste and a bunch of partners, and we had a working group to figure out how we could come up with a low embodied carbon concrete building code. And we had code officials and industry professionals and the concrete industry and policymakers, advocates, in work sessions that lasted over a year, just to come up with what is a code that could be kind of done and that a city would pass. And it wasn't always the easiest with the concrete folks in the room, but they had to be there. And so just trying, bringing together those multidisciplinary groups and just trying to change something, and sometimes really just having to stick it out, because policy change doesn't happen quickly, but it has to happen.
Thank you to all of our amazing panelists for this vibrant conversation. I'd like to open it up to the audience for some questions.
Okay. I do have a question, since we are talking about biomaterial, right? So it's agricultural sources. The variability in the sources, whether you grow it in different locations, even in one location. Some season you don't have rain, the other you have too much rain. You ended up with variability. So now going to the regulation, what does it mean? Do we need to increase safety factor to meet the regulation, or what can be done?
I'm sure you'll have more thoughts, but even with steel and concrete, there's still but I think you're talking about an enormous, a larger, so we're talking about a bell curve, right? it's gonna be a much flatter, wider bell curve and then looking at one. So but I think that there's probably more characterization that is needed and thinking like about the materials and differentiating them by their source, and then it does come down to separating in a way so that there is a bell curve that isn't going to force us to slap on an enormous safety factor that to encompass all of what we might think of as a material right now, right? So that's the just one solution that comes to mind of how to tackle that. But I totally appreciate like what you're saying with how much more variable these materials are. And the other aspect too is that there's we're used to, in construction, we're all kind of used to saying material as like a homogeneous at both in the chemistry and the like molecular, like the physical structure, you know, but I think that with biomaterials, there could be variability at different layers, right? Like you can talk about variation at something at the scale you can see, and then all the way down to like at the molecular level. And so some of the overcoming too is this like a bit of a assessment of, well, if you were to, you know, grind it, get it to be more homogeneous, like that input that as a raw material is still a better substitute often than fossil fuels. But you have to kind of keep calculating and checking that assumption, right? Like how much energy are you putting into this to make it more homogeneous? And then again, like what can become a bit later. You don't want to be mixing in things that where it becomes this, you know, has to go ways. So, but I think that also, you know, just approaching it about where is the variation happening? Is it at what scale is it happening? Can help address that too.
And perhaps just what I said a little earlier is sort of, well, what are you trying to substitute that biomaterial for? And maybe at something that is a very big structural scale, there will be fewer options because it has to serve such an important purpose where maybe the variability is too much without having to mix it with so many other composites that it's not going to be that much of a better solution. Although if you can get 50% carbon reduction from concrete, then that is good. So that's where, again, it's sort of like, what is the problem you're trying to solve and which biomaterial may be the best for that? Because, yeah, it's going to vary. And so maybe something that is a lot more inconsistent can be something else, can be flooring or furniture, but not the structure of the building. There's lots of different things we need redesigned. So all of these solutions can fit into one of them probably.
It's also possible, wait a minute, there it goes. It's also possible that what would be appropriate in one area might not in another. So you could end up with a biomaterial that would be perfect for some application in Arizona, for example, and it would not work at all in the Northwest. So just because it might not work everywhere doesn't mean it isn't got a great opportunity to do something useful somewhere else.
By the way, when oil was discovered, it was also variable, and they had to standardize it, hence standard oil. And so the same problem happened with that discovery, and all of the offshoots of products when they standardized, those sub-materials that were produced then got turned into other materials. So I feel like it's actually a precedent for the innovation we're experiencing here.
That's a great point, and the same thing is in steel. You can make steel alloys of hundreds of different properties, but the engineers don't want to have to figure that all out for every single project. So there's a default sort of AWS standard, or AWS, but ASTM standard property for what is considered structural steel. And then there's grade 2, 3, 5 bolts and that, but I mean, it's standardized and so it can be used everywhere. And that doesn't necessarily mean that that's the best material for a particular job.
Thank you.
Now I got the mic.
Green light.
Oh boy. This one's way down here. Thank you for the talk. I want to talk about code and changing how we address code. I'm a building contractor, so I'm also kind of from the industry side of it. And it seems like to speak to the prescriptive versus the performative, I think building a framework that allows us to adopt that kind of a model more is really important. Getting the other interests that are kind of like, hey, let's make this happen together, you scratch my back, whatever, quid pro quo. I'm wondering if you think that there's a way that we can say, we can kind of reform it and say, this is what the normal standards are, but if you want to do something else, here's the framework for the owners, the stakeholders, the engineers, and the designers to say, we're willing to understand the risks and take the risk on ourselves, whereby reducing some of the friction that is at the code level. And maybe municipalities don't bear the brunt of that risk in the form of lawsuits or taking, the health and safety risk. Maybe as a society, we get together and say, hey, you guys decided to do this.
Maybe quickly, you're gonna have a good answer, but I've gotta say that we did run into a situation where we had a client who wanted, I'm gonna tell you where it is or anything about it, because it's got a special contract that goes with it. But the client wanted a carbon fiber pedestrian bridge that was cantilevered, not connected to the deck, so it was tricky engineering problem. And it didn't, it wouldn't fit in any code. Oh, we wanted it light enough to carry through the living room and put it in the backyard. So it is possible if you get the right team together. And then we had structural engineers that were party to this, but the rules were written so that everyone felt safe in making that. It can happen, but it's one first time in 45 years.
Yeah, I think it's a hard, it feels sometimes that the legal system here favors all kinds of trivial lawsuits, even when you've written agreements. But I know that from personal experience, I've had lots of things made, and I've basically given the manufacturers and the engineers, all the papers they wanted to say, I will never do anything about it. It's big European, it's not in my personality either. I mean, but one solution which I like, I don't know if you know this, but in Switzerland, the highest amount of money you can ask in a lawsuit from any industry is 10,000 Swiss francs.
Free for all.
And I don't think Switzerland has a reputation for being particularly, full of risk and full of problems. But I think the sort of space in which we evolve here in the U.S. Makes risk-taking in construction and material protection, pretty hard to take on, especially if you're a contractor and a builder.
Yeah, we deal with risk all the time, so someone's assuming it, local municipalities are, and this is why it's hard to innovate.
Yeah, I agree. I think you guys said it. It's hard. So, like you said, on paper, like we've seen some risk share contracts, right? But yeah, from what I hear, it's not the foolproof way through that. So you could still, yeah. But I think as a starting point, I've also heard there's something called pain share, gain share. Yeah, that if there's some kind of benefit that the owner or if it's who's presenting this alternative, the more innovative solution, and there must be some benefit, but if they need to help share that.
I think we have time for one more question. Anyone else has? Thank you for the conversation today. Really quick question. I think like the issue we're talking about of locality is super important, right? So like every locality will have different biomaterials that are available and that are useful for that region. So I guess my question for you would be, in California, in the Bay Area, what do you think is the number one biomaterial you're looking at that you think could be viable in the next, like, 5-10 years? Thank you.
You mean produced in California?
Produced in California or used in California is what I was thinking.
Well, so I guess that's what, Arab had the opportunity to work on with stock waste and look at the report about especially agricultural waste. And what's nice, it's not only a bio-based material, but it would be a waste product. So it's like a twofer. And what kind of came to the surface, straw was really strong. And it's great to see there's some, the collaborations happening now with the startup that you can see in the exhibit. And in different forms, right? Like we also see there's some success with straw as a compressed board. And as well as the one you'll see is a straw as a fill within a pre-panel. There's also straw blocks. There's straw. There's a straw MDF that was alive for a flash before COVID really kind of took them down. But I really love to see what happens with straw. But some of the others, bamboo or Bamcor is all over the exhibit, and that was, is notable in how much is produced and can become waste. So I saw though that I think in the diagram that what was pulled out of the report, and it was probably really special for California, is vines and orchard waste. If we could kind of tap into that and find a good way to channel that into construction products like that. Another challenge, that's an opportunity.
I'm not sure about maybe how viable it is, but I know one of the materials in that report as well that is top of mind is also fire damaged wood. We also have a lot to deal with it now in Southern California, and so when again we think about the issues that we're facing in climate change and things like that, it's an inconsistent product. It's not always available, thank God. Or hopefully it's not always going to be available, but there is a lot of it in the state. And so I'm interested to see what winds up kind of happening with that. But that's another one of the materials talked about in the report, that is sort of a unique opportunity in California to use a product that we're all really familiar with, but perhaps, again, not in so much, well, in some cases, perhaps a structural application, but just going back to like, how do we use these really resources that we have in front of us to the highest and best use that we can.
Yeah, and in addition to fire damage, the fuel reduction projects for the woods that have been on fire yet, but there's a lot of, that Cal Fire, there's so much that's attention towards getting the fuel out of the entrance.
I think to me, this, all this talk about mycelium was interesting. Because what we learned about that, we've been working with Autodesk on that project, and you need a matrix of some kind in addition to the mycelium, such as pure mycelium. It's like straw, or switchgrass, or something agricultural waste like rice hulls maybe, and then and I saw today the big problem we've been having is getting shear strengths out of mycelium products, but I saw there's some much denser mycelium that looks to me like it could work, and if that happens, that could be a big deal. I mean, that.
Say almond hulls.
Almond hulls. Yeah.
Maybe pistachios.
Bean curd is a good
We have one more question in the front.
No, I have a clarification question. Is it for the embodied energy in US, when you reuse the material, does it go to zero as a metrics? You know, I heard that in Europe, for example, if you use a recycled glass, the embodied energy start from zero. So you count from, you know, and after that, whatever you're adding, it becomes your embodied energy. In US, I heard that they count the previous life of the material and add up. So for example, a recycled glass already have this much embedded energy and it does. And I think that's one of the aspects that it doesn't encourage people, for example, that reusing, you know, reusing material, but at the core, you know, as a metric, you're not getting that much advantages. So it was this is not a question, I'm wondering that, is it true or is it?
Yeah, I think in life cycle assessment, there's a few different allocation models, but I think what you're talking about is when the material is characterized as waste, then when it enters a new life, that you could, start at zero. We still have to add all of the energy and the processing that would be needed and transport emissions from those activities. But whereas there's another allocation where even if it's like a waste, then it still has to carry like the either proportioned by the cost, an economic allocation, or by mass, or by like there's some allocation that even follows all the way to, even though it's considered a waste at the end, just because because it's going to be used again. It's so it's not really waste, but is that what you're talking about? I think it all depends on the definitions with waste though. Like so, for instance, fly ash and slag, even though they're widely used now in concrete, like they get to take that zero benefit. Yeah, they could start at zero, and there's a lot of debate about whether that should be allowed. Thank you.
Thank you so much, Francis, Phil, Eve, and Emily, for sharing your experience and wisdom. And next, we'll have our keynote speaker. Did you want to?
Thank you.
Everyone, yikes. I just want to say a few words. We're going to take a short break and then come back at 5 for the keynote with Lynn. But I wanted to thank all the panelists for the 3 panels today, because there might also be some people not making it. I hope everyone stays for the keynote. But also, like, the panels were so inspiring to me and connecting dots, not just about what we've seen in the great work that Margaret and Evan and Alex and Nagar put together with our amazing students, but things that are also happening in other spaces in the program. I really would invite you all, if you have thoughts about working with us, connecting with us, like reach out to these amazing event conceivers, creators, logisticians, or to anyone else on our faculty. Like grab someone who looks like they might be involved in CCR community. Say, I have an idea, like we want to hear those ideas. We want to work with you. Emily and Francis, like I was just leaning over to Alex and saying, I have an idea. So thank you all so much, and join us back in 15 minutes.